Hello class, welcome to lesson 3-4, which is all about direct variation. By the end of this lesson, you should be able to write and graph direct variation equations, and you should be able to solve problems involving direct variation. So first of all, something that you need to know is the direct variation equation, which is represented by y equals kx, where k does not equal 0. And then the constant variation, or it's also known as the constant of proportionality. You'll hear me refer to it as the constant variation more often than the other one, but that is represented using k. Oh, and one last important thing that I forgot to say about direct variation, k will never equal 0 in a direct variation equation. So let's look at our first example. We want to name the constant of variation for each equation and then find the slope of the line that passes through each pair of points. So first, if we look, at letter A we have y equals negative 4x. And remember, our direct variation equation is represented by y equals kx. And k represents our constant of variation. So if we look at our equation, we know that our constant of variation equals negative 4. And then we need to find our slope. So if we look at our slope, we are supposed to take the two given points. So we have 0, 0 and negative 1, 4. So my slope, remember, slope is rise over run. If I go up 1, 2, 3, 4, and then left 1, so that's a negative 1, my slope also equals negative 4. Okay, so you can see those ended up being the same. And if we look over on the right hand side, our equation, y equals 1/2 x, so our constant of variation is going to be 1/2. And then our slope, we go up 1, 2, 3, and we run to the right, so positive 1, 2, 3, 4, 5, 6, which that means our slope is 1/2. So hopefully you see the pattern of constant of variation and slope end up being the same thing. Go ahead and try this next one on your own, see how you do. Hopefully you determined that the constant of variation was negative 3 and the slope was negative 3. If you have questions about that, be sure to ask in class. Example 2, we want to name the constant of variation for y equals negative 2x, then find the slope of the line that passes through 0, 0, and 1, negative 2. Okay? So if we have our equation, we already have our constant of variation, which was negative 2. And then if we find the slope, that means I need to do my y2 minus y1 over x2 minus x1 when I have my given points. So I take my, I'm going to call this x2 and y2. So I have 0 minus a negative 2 for my y, and then I have 0 minus 1, so this becomes 0 plus 2, which is 2, and then 0 minus 1 is a negative 1, so our slope is negative 2. And if you look, our two numbers end up matching. Next, we want to name the constant of variation for y equals 1/4 x. So I already have my equation, so I know my constant of variation is that number connected to my x, so that should be 1/4. And hopefully when I figure out my slope, I end up with the same number, but let's double check. So this time I'll say this is x2 and y2, x1 and y1. So if I do y2, that's 1 minus 0 over x2 is 4 minus 0, so that is the same as 1/4. So our constant of variation checks out to be the same thing as our slope. All right, so example 3, let's graph the following equations. Let's practice some graphing. If I look, I have y equals 6x. One important thing to note about direct variation is it always goes through the origin. Okay, so it always goes through that point 0, 0. If we plug 0, 0 in, so if we plug 0 in for x, so 6 times 0, does that equal 0? Yes. Okay. So you're always going to have the origin in a direct variation equation. So I'm going to start by plotting 0. Then if I plug 1 in for x, 6 times 1 is 6, so I can go up 6 after going to the right one. And if I were to plug in a negative 1, I could go left 1, and then that would be down 6. So 1, 2, 3, 5, 6. And then I'm going to do my best to connect these dots in a nice straight line, but I'm not using a ruler or anything, so it's not my straightest line, but it works. Let's look at y equals 2/3 x. Again, we can start at that origin, so 0, 0, and if I plug in, let's see, what would be a good number? I know if I multiply 2/3 by a 3, that means my 3's cancel, and I'm left with a nice 2. So I'm going to try going to the right 3, and then that means I go up 2. Or I could do the same, I could do a negative 3, so then I would have a negative 1, and then a negative 2. So I could go left 3 and down 2. And there's 3 points I can use to graph my equation. And let's try the last one. We have y equals a negative 5x. Again, start at the origin. If I plug a positive 1 in there, I'm going to have to go down 5. If I plug a negative 1 in there, I can go up 5. And when I say plug it in, I'm sorry, I should be saying plugging it in for x. I was getting a little bit lazy there. But those would be the 3 graphs for those equations. So why don't you go ahead and see how you do with graphing this equation here. Hopefully you determined that the answer would be letter B, or graph B. And then a few items to note about direct variation is direct variation equations are always, always, always of the form y equals kx, where k cannot equal 0. It always passes through the origin. If it doesn't go through the origin, that means it's not direct variation. Okay? And then whenever it's positive, your slope will be facing this way. If k is greater than 0. If k is less than 0, that means your slope is going to be, the slope of the line is going to be negative, and it will look like the graph on the right. All right, let's look at example 4. Suppose y varies directly as x and y equals 98 when x equals 14. Write a direct variation equation that relates x and y. Okay, so just like I just said, we always write direct variation in the form y equals kx. Okay, so in this instance, the example didn't tell us what our k value is. It didn't tell us our constant of variation. But it did give us 2 numbers. It tells us when y equals 98, x equals 14. So I can say k, and then I can plug a 14 in for my x. If I continue to solve that, I can figure out what my k value is. So if I divide by 14, I'm left with 7 equals k. So I have my constant of variation. That means I can now write my equation as y equals 7x. That would be my direct variation equation for this problem. And I can then use that to find y when x equals negative 4. So I can say y equals 7 times a negative 4, or y equals negative 28. So why don't you guys go ahead and try this next problem on your own, see how you do. Hopefully you ended up with y equals 3x. If not, be sure to ask myself or a friend. And let's look at our last example. So example 5, the Jones family is driving cross-country on vacation. They drive 330 miles in 5.5 hours. Write a direct variation equation to find the distance d driven in time t. So, first, direct variation equation. We want something that is of the form y equals kx. Do we know what our constant of variation is? No, so we have to solve that. The only two things we know are 330 and 5.5. Now, you might be asking, how do I know which one to plug in for x and which one to plug in for y? Remember, we talked about in Chapter 1 dependent and independent variables. We said that independent variables are always the x-axis and dependent are always the y-axis. Then, after we determined that, we said that time is always an independent variable because we can't change time. Time will always continue to go whether we want it to or not. Okay? So it's independent of everything. That means our independent variable is the hours, and that represents our x. And then the miles would be our y. So we can say 330 equals k times 5.5. And then if we go, we can say 330 equals k times 5.5, or if I divide both sides by 5.5, I end up getting k to equal 60. Okay? Then I could go ahead and write my direct variation equation. I could say y equals 60x. Or since I'm talking about distance and time, remember the equation we learned in Chapter 2? We said distance equals rate times time. So instead of using y and x in this instance, I could use d equals 60t. And that could be my equation. But that's just using other variables, okay? It's not really changing the integrity of the problem. Now, if we want to graph this equation, as we mentioned, time is always going to be our x-axis, so we can say time is over here, and then miles, or distance, is going to be over there. And if we have 1, 2, I'm going to quickly label my graph so that way I can determine what things should be. So then 100 miles, 200 miles, 300, 400. Okay, that should be enough labels to help figure this out. If I want to graph this, so at 0 time, no time has passed, we haven't made it anywhere. After 1 hour, we will have made it 60 miles, right? Because we plug 1 into our equation. After 2 hours, we will have made it about 120. It's going to be up in here. And 3 would be 180. 4 would be 240. 5 would end up being 300. Okay, and I now have a nice number of points that I can go ahead and graph and draw my line. Okay, so then if I use that, I want to estimate how many hours it would take to drive 500 miles. So if I use my graph, I made it large enough that I can hit the 500 miles. Then if I go, my graph isn't great, but it looks like it would end up being just over 8 hours. So let's test that algebraically to see. So we know d equals 60t. We want to know how long will it take to go 500 miles. So that was bad 0. We can plug 500 in for d. and then solve for time. So I can divide both sides by 60, and I get 8.33 hours equals t. So about 8.33 hours to go the 500 miles. Okay, so why don't you guys go ahead and try this last example on your own and see how you do. Hopefully for letter A, you determined that the equation would be D equals 8H. And then go ahead and try the next one on your own, see which graph you determine. Hopefully you chose the letter C graph. And our last one for you, estimate how many hours it would take to jog 16 miles. Hopefully you ended up saying 2 hours. But if not, if you have any questions on anything in this lesson, be sure to ask either myself, a friend, email me, come see me in the morning before school. Just make sure you understand this. Have a fantastic night.